Hello, everyone. My name is Francisco Bernardo, and this is my ADC presentation, Driving Chaos, Virtual Analog Modeling of a Chaotic Circuit with Wave Digital Filters. A little about me. I'm a research associate in digital musical instrument design at the Augmented Instruments Lab and the Dyson School of Design Engineering at Imperial College of London, who graciously supported my participation at ADC this year. I have a background in computer science and systems engineering. I was a software engineer in the industry for many years before my PhD. I'm a multi-instrumentalist with a concentration in guitar, electronics, live coding, and experimental music. And currently, in my research, I'm focusing on hybrid analog-digital audio effects and embedded computing. As part of my research, I've had the opportunity to explore virtual analog modeling techniques such as wave digital filters, and I found this interesting connection between nonlinear dynamical systems and virtual analog modeling. There have been past ADC sessions that have addressed these topics independently, but I thought I could make a small contribution to the ADC community based on some of my early exploration and provide a quick entry point with an interesting example that links both chaos theory and wave digital filters. So, following the motivation, I will provide brief introductions to chaotic systems, to virtual analog modeling with WDFs, and then we'll do a walkthrough of the modeling and implementation of the Chua circuit with WDFs, and followed by a quick discussion about the applications of the wave digital Chua circuit as a chaotic signal engine for applications in music and audio, and finally we'll conclude. Chaotic systems are deterministic, nonlinear, dynamical systems. Dynamical means that they have behavior or state that changes over time. For instance, these variables, x, y, and z, they're the state of a system. Deterministic means that their state change is governed by a fixed set of rules, such as this system of differential equations. And nonlinear means that there are relationships between the variables that are more complex than linear, such as the multiplications between x and y and x and z. So this is the Lorenz system, a simplified model of an atmospheric phenomenon called convection, which is how the air moves when heated from below and cooled from above. If we solve this system of equations for specific initial conditions and for many points in time, and we plot the solutions in what's called the state space, what we get is all these trajectories or orbits. These trajectories are the sets of all possible system states that specify instantaneous conditions over time. The Lorenz attractor is this set in the state space to which all these trajectories are attracted to. And that forms an invariant of the system, so it doesn't change. So this butterfly-like image of the Lorenz attractor and a paper that Lorenz published later titled, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" is what actually helped to popularize chaos theory as the butterfly effect. Chaotic systems have interesting properties. For instance, repeatability. Given the same input, with the same rules for different runs of the system, you always get the same outcome. If you reset the system exactly the same way, it does the same thing over and over again. Also, short-term predictions are possible. However, over time, tiny differences will blow up. This is because of the gradual accumulation of precision error over time, and also because of the property of sensitive dependency on initial conditions. Chaos looks messy, but there is actually an hidden order, an emergent structure with fractal qualities and repeatable patterns. Chaos does not behave like noise. It's interesting to contrast deterministic chaotic systems with indeterministic systems, such as stochastic or probabilistic systems, which have no rules and there are always different outcomes for different runs. They are truly unpredictable beyond their statistical properties, such as the distribution or the mean or the variance. They show no structure whatsoever, with some exceptions to in the spectral domain. There are two very good ADC talks about chaotic systems that I would like to refer to. The first covering the mathematical and physical foundations of nonlinear oscillators, and the second one giving examples of chaotic systems in audio, such as in analog synths, VST plugins. And they also cover some of the general theory in chaotic systems and provide examples of interactive sonification. They barely covered the Chua circuit, which is the next chaotic system that I'm going to talk about. The Chua circuit is an analog electronic circuit designed by Leon Chua. It is one of the simplest electronic circuits exhibiting chaotic behavior and yielding very stable attractors. It comprises two capacitors, one resistor, an inductor, and a Chua diode, a nonlinear negative resistor. The state variables of the system are X and Y for the voltages across the capacitors C1 and C2 respectively, and Z for the current through the inductor L. F of X is a piecewise linear function, a nonlinearity that models the current voltage relationship of the Chua diode, contrasting to the resistor's current voltage relationship, which is a line crossing the first and the third quadrants. You may see that with the Chua diode, this relationship is inverted, which makes it an active element. And also, it's composed of three segments with two slopes, GB and GA, which confers the nonlinear characteristic. You can see on the left panel a Python implementation of the Chua system with the constants, the variables, the Chua diode nonlinearity, and the system of ODEs. The traditional approach to find solutions to nonlinear ODEs is to use an iterative solver, like the Euler methods, the Newton-Raphson method, or the Runge-Kutta solver. We're using the latter here. I'm initializing simulation parameters with initial state and time span to the explicit Runge-Kutta method of fourth order. The result, which you can see on the right, is the time series for the state variables, the capacitor's voltages, and the inductor current. If we plot them in three-dimensional state space, we get what it's called the double scroll attractor, which is characteristic of the Chua system. We can also see the XY, XZ, and YZ projections of the attractor on the bottom. A good thing about the Chua system having a piecewise current voltage relationship is that it can be solved in the wave domain. So we can take advantage of this and implement it with wave digital filters. WDFs were developed by Alfred Fettweis between the late 1960s and the 80s, originally for modeling digital filters by discretizing reference analog circuits. Nowadays, WDFs are considered a white box approach to virtual analog modeling because physical interactions between the circuit components are what's modeled and computed. This is in contrast to black box methods, where a system is learned from a set of inputs and outputs with a neural network, for instance. So in this approach, circuit elements and topology are modeled explicitly and separately. Elements are discretized independently and connected as nodes in a tree structure, and topology is modeled using scattering junctions with wave variable parts with incident and reflected waves. So this is very applicable to simple circuits like the Chua circuit. But in the last 10 years, research has developed this approach and made it more generalizable and powerful. Here's a list of academic literature covering the original FAT-FICE reference and papers that push WDFs to their modern shape. Also, a few PhD theses where major extensions to the framework were created, like Kurt Werner's, which provides a good tutorial and a great reference for deriving WDFs. François Germain about digitization methods, and Gianpiccolo with very interesting applications of WDFs to multiphysics problems involving transducers, speakers, and circuits. The second paper is an oldie and one which we are going to follow to implement the Chua circuit. There are also good introductory talks to WDFs by Jatin Chaudhary and Chris Clark, and Ricardo Gianpiccolo's talk that provides a great overview of WDFs and the most current trends in WDF development. There are also software libraries that you might want to use if you don't want to reinvent the wheel, of course. Many of them are C++ libraries, more oriented towards performance. For this presentation, I used the last one, PyWDF, which is a Python package which is very good for prototyping. I have my own fork of the library, which you might want to look at if you want to follow or test the Chua circuit examples. The Muir-Kutter and Scholl's paper provides a wave digital model of the Chua circuit with the elements, adapters, and parameters, as you may see on the left. We'll use it to guide the implementation of the Chua circuit class, which inherits from a PyWDF core class circuit. First, we establish the connection tree here on the bottom with the Chua diode at the root of the tree. We will look at the Chua diode implementation in a minute. We parameterize the Chua diode with the suggested values, and we pass it a parallel adapter as a child reference. The parallel adapter, in turn, connects capacitor 1 and series adapter as child references. In the model, the series adapter connects parallel adapter 2 and resistor 2. Now, this is a decision that required some exploration. We need to excite the circuit with voltage impulse, and connecting a resistive voltage source will allow us to achieve that and still have the specified resistance in place. Parallel adapter P2 connecting the remaining leaf nodes, capacitor 4 and inductor L3. And this is the easiest way to implement the Chua circuit. An alternative way that maintains the original configuration of elements, that is, resistor 2 instead of replacing it with a resistive voltage source, is to add an exciting mechanism to the circuit by creating a new adapter, a two-part adapter, a series voltage. This allows us to keep the configuration and inject a voltage impulse in the circuit to excite it. So here we have the original leaf nodes and the series voltage adapter. We'll see the implementation in a minute as well. In order to extract our signals of interest, the X, Y, and Z of our chaotic system, corresponding to the voltages across the capacitors and the current through the inductor, we need to adapt an asynchronous handler that WDF provides us to probe specific elements that have been stored in the tree structure. This required extending the WDF library with getters that not only convert from wave digital to voltage, but also to current. A small detail. So now we can return a tuple of the signals of interest. Now let's look at the Chua diet class implementation, which as a nonlinear, non-adaptable node has to go into the root node. So it inherits from root WDF. So besides the constructor and connection to child nodes and parameter storage, what's really important is how the conversion between wave digital and kickoff domain happens. And this is where it happens, and it's also where the piecewise linear function is implemented in the reflected wave member. Series voltage is the adapter that allows us to inject the voltage impulse while keeping the original element configuration. It has to implement the behavior of an embedded source that sets voltage, but also of a two-parts series adapter, which allows that voltage to affect the child and its parent through the incident and reflected parts. Finally, the main function, which is very simple. We set a sampling frequency, which is necessary for the reactive components, which have local discretization. And here we need to oversample to about twice the audio rate. So here I set it to 100 kilohertz. And I instantiate a Chua circuit with that frequency. I create an impulse signal to excite the circuit. And then I just do sample by sample processing of that signal and collect my signals of interest for plotting. So what we're going to see now is our WDF Chua circuit running in different modes configured by one single parameter, the value of resistor R2, which you can think of as a potentiometer. So in the first plot, R2 is at 1.85 kiloohms, and it shows a fixed point attractor evolving towards the steady state, so a very stable mode. In the second plot, R2 is at 1.55 kiloohms, and it shows a loop, so an attractor very close to periodicity. So still stable, but not so much. In the third plot, R2 is at 1.45 kiloohms, and it shows a double scroll attractor, which means that our system is now an engine driving chaos. So now that you have a chaos engine, what can you do with it? There has been a lot of exploration in the 90s of chaotic signals for music and audio. At the music level, that is, at the level of note events, it has been used for creating variation, transitions between motives and repetition and variation or inexact patterns. Truax makes nonetheless a very important point. Arbitrary mapping of a nonlinear function onto a sequence of pitches might not be more musical than purely random processes, which can be quite boring or dry or meaningless. So what is important is how the mapper knows his mappings and how he applies them. And the predictability of a chaotic signal might be useful for that. At the sound level, at the level of sound synthesis and timbre construction, you can have many things: cross-coupled modulation, chaotic FM, chaotic AM between synchronized oscillators, control of music parameters with mode changes, applying unpredictability to granular synthesis, grain selection, and so on. So this has been my presentation covering these properties of chaotic systems, these techniques for modeling a chaotic system, the Chua circuit, and a very quick discussion about the potential application of it. Thank you for your attention and drive safely.